We introduced PartAfford, part-level affordance discovery from cross-category 3D objects. Previous work in passive affordance learning mostly follows the supervised learning paradigm. Instead, human beings could learn affordance from very sparse annotations. We could intuitively ground affordance to part geometry by learning the contrast in affordance composition and geometry. To make a shift of passive affordance learning from dense supervision to sparse supervision, we propose PartAfford. The model is tasked and trained to learn object affordances with natural supervision of per-shape affordance label set. At test time, it could decompose 3D shapes into parts and discover how each part corresponds to a certain affordance category. We construct the part affordance dataset, where we annotate 24 kinds of fine-grained affordance labels on over 25,000 shapes across 24 object categories. The PartNet dataset does not contain articulation information. Thus, we use Sapien and annotate the openable affordance at different articulation states. Utilizing the part affordance dataset, we propose a novel framework for PartAfford. Our model contains two main components, an abstraction encoder for part-centric feature extraction and an affordance decoder with 3 branches. Given an input shape, the abstraction encoder extracts part-centric features, which are also known as slots. For example, there are 4 slots. In the iterative slot attention module, the inputs to slots attention assignment is normalized over the 3D slots, thus those slots compete to attend to a clustering of the input 3D shape. Given the part-centric slots features, 3D part reconstruction decoder learns the part-level segmentation from the self-supervision of 3D reconstruction. Affordance prediction, the second branch, discovers the corresponding affordance for each slot with set-based matching loss. It helps to learn part affordance correspondence from the contrast in affordance compositions. Cuboidal primitive regularization, the third branch, predicts a cuboid for each part. The joint loss ensures part cuboid consistency by fitting the reconstructed parts with cuboids. Quantitatively, on the constructed part affordance dataset, our method beats all SOTA and ablation methods by a large margin in the core part discovery metric and also outperforms in the 3D reconstruction metric. Qualitatively, on sittable associated objects like chairs and sofas, each object could be segmented into a proper number of affordance parts with tightly wrapping cuboids. Such results demonstrate the efficacy of the proposed method in the challenging sparse supervision setting. By contrast, the unsupervised SOTA method suffers to segment parts from similar object shapes.